All right. Good, time to start. And we start from announcing the first thing, which is exam number 3. It's coming up next week, exactly this time, Thursday. But no, let me correct myself, not exact this time. We'll be starting the exam 10 minutes earlier so that we do not delay and overflow to Professor Wang Hui's lecturing. Okay. So the details will be in the channel, exam 3. Okay, so you see already the exact date and time and the scope of the exam, which is essentially chapter 3. And of course, the link for the remote student to join for the video session and the link for the exam. Okay, it's going to be, again, a Google form. Good, now let's close our Slack and move on to the lectures. And we'll start from here today, okay, talking about, finally, the congestion control in TCP. Well, as you heard at the end of Tuesday, so what TCP is doing is exactly guessing, okay, what is the right sending rate, okay, to avoid congestion. So the idea here, very simple. Sender will try to increase the transmission rate until there is a loss. So if everything goes well, then the sender will continue to increase the transmission rate. Okay. Recall quiz 22, right? If I say too low, yeah, I recall team 5 and team, I think 7, right? Continue to guess a number that's higher. Until I say, too high, then they would start dropping the gas. So it's very similar. Sender continue to increase until there's a loss. Whenever there's a loss, that's an indication of congestion. And by the way, when I say transmission rate, okay, in TCP, okay, the variable that captures the transmission rate at the sender side is exactly the window size. Oh, okay, so the window size can be changing, increasing. Later you'll see it can also be decreasing. Now the way we are increasing it is, to be more precise, this. Additive increase. So we'll increase the sending window size, which by the way is represented by this variable, cwnd, standing for congestion window. So this is going to be incremented by 1 maximum segment size for every round trip time. Okay. So recall again still, TCP is something like go back in, where we pipeline multiple packets in 1 round trip, right? So multiple packets in 1 round trip. The way TCP sender is increasing the congestion window size is after 1 round, meaning 1 round trip time, increase, okay, the window size by 1 packet. Okay. Now this will be done continuously. Okay, if the packet transmission goes really, really smooth, 1 round trip time, 2 round trip time, 3 round trip time, the window size will be incremented by 1 packet, 2 packets, 3 packets continuously until there's a loss. So if there's no loss, the increment will continue to go. If there's a loss, okay, after detecting a loss, the congestion window size will be dropped to half. So what I'm drawing down below here, okay, is a graph where the x-axis is the time. Y-axis is the congestion window size. So it will look like this. The congestion window size, when there are no packet loss, will continue to increase additively, linearly, until there's a loss. Then the window size will drop quickly down to half of the current window size. But if X continue to come in, then we continue to increase additively until the next loss, then dropping back window size back down to the half of it. Okay. So this is going to go on and on and on. Okay. Do you find the shape of the curve looking like something? It is, right? It looks like a sawtooth. And so from the curve, you also see the increase is additive, linear, growing. Decrease is multiplicative, okay? Having it each time, there's a loss. So altogether, additive increase, AI, multiplicative decrease, MD, is the term we use to characterize how TCP adapt the window size, okay, to congestion. You see also, this is how TCP is guessing, okay, or probing to discover what is the best transmission rate. What should be the best transmission rate? We don't want to send it too low, right? Because that would be too slow. But if we send it exceeding the capacity, okay, of the links that the traffic is going to go through, we also get packet loss. So what is the best rate? The best rate will be the available bandwidth from end to end, isn't it? So going up and down and up and down and up and down is how TCP is guessing what is the right congestion window size. So in a way, TCP sender is playing the congestion window is right game all the time. Okay, so in that quiz 22 experience, when poly is saying too low, right? So the students get a higher value. So continue to receive acknowledgement packets, not detecting any loss, it's like poly saying too low. Detecting a loss, it's like poly saying, hey, too high. The difference is, however, that when we're doing quiz 22, your students are, guessing it based on their own strategy ad hoc. But TCP follows specific principle. Okay. Now, this slide is to enforce this. Okay, congestion window size. Wait a minute. Window size. We've talked about window size, right? In go back in. Okay, in also the simplified version of TCP where we only have reliable data transfer. So what was the window size then? At the time, it's this, right? The entire area containing the yellow bytes as well as the blue bytes. So yellow bytes are the bytes that are already sent but not yet acknowledged. And the blue ones are what? Usable, but there's no need of using it because there are no more data coming from the application layer. So cwnd, is exactly the window size we've been talking about. Okay, so this is just to enforce so that you know what cwnd is. The weird thing happening here now is just that the cwnd can change. Unlike in go back N or simplify TCP, it seems to be a constant, a big N if you recall. All right, so the sender is actually limiting its transmission by this. Last byte sent, so which is this, the last of the yellow. Last byte acknowledged, the last of the green. So the yellow area must be below the congestion window size, of course, isn't it? And so when we are sending data from the sender, okay, it's initiated by having a call from above saying that I have data to send. Before we actually generate a packet to send that data, we check what? We check next seek num, which is the first blue byte, plus the data size, whether it exceeds this value as well, isn't it? Yeah, so still, sending of these bytes is bounded by the cwnd, all right? The only thing that's being different is just that cwnd is now dynamic, okay? And how? We just talked about it, AIMD. In congestion avoidance state, increasing the window size is for each receive acknowledgement and every round trip time at 1 packet. Sorry, so let me clarify that. After receiving acknowledgements, meaning no loss, right? For each round trip time, additive increase. Now, hey, you're seeing Polly writing quite a bit of things here, okay? It looks like, oh, congestion avoidance is just a part of TCP's congestion control. Well, you're right, because there's also another part. So congestion avoidance is the steady state of TCP. Okay. When the TCP connection is just starting, which window size should it start, right? So for the initialization, for the beginning of the connection, we talk about this other mechanism, so start, which is coming up next slide. Okay. Now, the last bit that I haven't really quite covered on the slide is just this. Because we send one flight of packets, which is the cwnd within 1 round trip time. So the transmission rate is essentially congestion window size divided by round trip time. Now, slow start. So this is the behavior of TCP sender at the beginning of a connection. So we still increase the window size when there are no loss, but we actually increase it this way, exponentially instead of linearly. So to be exact, the pseudocode looks like this. We start by setting the initial congestion window size to 1 packet. And each round trip time, we double the window size. So, hey, in the next round trip time, what should be the window size? 2 packets. Yet another, 4 packets. Yet another, 8 packets. So that's what I was illustrating here. First round, window size is 1, so we send 1 packet getting 1 ACK. Second round, window size is now 2, right? 2 packets. Third round, double 2, meaning 4, like that. So it's actually increasing really fast, although we start from a very, very low value. Okay. So don't be confused. Slow start here, the slow here actually meant to refer to this 1 here. Okay, we start from a very, very low number. Okay. But the increase of the window size is actually much faster than in the steady state. Can you imagine why? You can probably imagine why, right? Because this is a very low value, 1 packet. TCP's maximum segment size is only 1,000 byte. So that's 1K byte. That's very low value. So in the initialization phase, TCP sender tries to be aggressive increasing, even though starting very, very slow. Now, this is very important, okay, bullet number 3 here. Okay, how do we double window size after 1 round trip time? I know, you might be thinking, oh, wait, hey, right? We could set up a timer here at the sender, right? Count for the estimated RTT, right? And then add the window size. Okay, and double it to 2 times, right? So this is one way. But the way it's implemented in TCP is this. It is implemented this way. For every acknowledgement packet it receives, it increments the window size by 1. Would that work? Let's look at the diagram again. Sender here, window size 1, send 1 packet, 1 ACK comes back. Increment window size by 1, so window size now is 2. So we can now send 2 packets in flight. 2 ACKs will come back. Oh, each will increment the window size by 1, so 2 plus 1 plus 1, because there are 2 ACKs. So we have 4 now. We get to send 4 in the flight, and 4 back. So 4 plus 4, oh, cool, 8. So by implementing, the sender this way, reacting to receiving an ACK, we actually managed to achieve the same thing, doubling the window size, each round trip time. You know what? That's exactly also how we implement AI in the sender. But the increment must be different, right? Upon receiving an ACK, TCP sender in the congestion avoidance state, does it increment the window size by 1? No, I see you shaking your heads, right? Because obviously, if you increment the window size by 1 per ACK, then you are doubling the window size. That's too aggressive. That's not AI. That will be EI, right? So Start is doing it that way. Okay. So in AI, what should be the increment? What was AI doing? Every round trip time adding by 1 packet size. Okay, then we ask, right? How many ACKs there are within 1 round trip time? How many? The window size, isn't it? Window size divided by the maximum segment size. cwnd, well, we're counting bytes, right? So how many packets there are? MSS, right? So this is the number of ACKs we'll be receiving within a round. So the goal is that after receiving all these, window size is incremented by 1. So for every ACK, how much do we increment? The inverse of this, right? So for each ACK, we increment this amount. Because there are these many ACKs arriving each round. So for each ACK, we can only increment this much so that it will multiply to 1 after receiving all the ACKs. Okay, so remote students, you probably don't see, but okay, so similar. At the congestion avoidance state, the adjustment is still being done after receiving an ACK. Okay. But the general idea is that after a round trip time, additive increase and exponential increase, for congestion avoidance versus slow start states. Okay. Now, so slow start talks about increasing. Congestion avoidance states talks also about increasing, but congestion avoidance states talks also about decreasing, the congestion window size. Now, to be exact, how TCP is decreasing the window size is slightly more complicated, Well, we know that whenever there's a packet drop, we need to decrease, or packet loss, we need to decrease the window size. But you see, there are 2 ways of detecting packet losses, isn't it? One is, if you recall fast retransmission, by receiving 3 duplicate ACKs, we could actually quickly retransmit the lost segment. So we don't have to wait all the time, for a timeout. You know what, in TCP, the sender tries to differentiate, how serious the loss is. So which one do you think is more serious? Yeah, obviously the first one, right? This means there's not enough duplicate X at all. This means that at least there are still some packets going through and some acknowledgements coming back. It's not all that bad. So the decreasing strategy, therefore, also depends on how we detect a loss event. So let's talk about the straightforward one. So in case the loss is detected from a timeout event, then the window size is dropped all the way to 1 packet size. The window size will continue to grow if there are no more loss. And it will grow, look at this, exponentially, much like in slow start. Okay. And this will go on until the window size reach a special threshold called the SS threshold. This is the slow start threshold. So this is the threshold to define. If the window size is below that threshold, the TCP connection is in the slow start state. Beyond the threshold, that means the TCP enters the congestion avoidance state. Okay? So in a way, let me just write it over here on the board. So this is enabled by checking whether the window size is below or above the SS threshold. So after the window size go beyond the SS threshold, then we go what? Additive increase. Below that, working like slow start, exponential increase. So the other situation is the 3 duplicate ACK type of loss. So this is considered a slightly less worse situation, slightly better situation, because the network is still capable of delivering some segments, although the one that's missing somehow get lost. Okay. So the window size is no longer cut all the way down to 1, but only to half of the current size. And immediately, the window size grows linearly. So this is why you see I wrote down the whiteboard. If it's timeout kind of loss, drop the window size down to 1. If it's 3 duplicate ACK loss, drop the window size to half of it. Okay. And by the way, the whole set here that I'm showing you, this is implemented in the most up-to-date, the most recent TCP protocol standard called the TCP Reno. Okay, so this is something that I wrote here. So TCP, instead of calling the versions by counting a number, for example, TCP version 1, version 2, version 3, the designers seem to prefer giving them names. So TCP Reno, okay, is the name of the latest TCP protocol implemented in most operating systems, Linux and Windows. Okay, and the TCP Reno is also the default TCP protocols being used. There's the oldest version of TCP is called this, Tahoe, TCP Tahoe. So Reno, Tahoe, these are all vacational locations in North California. I guess the designers live in San Francisco or Bay Area. Okay, so Tahoe here, no matter what kind of losses, whether it's due to timeout, whether it's due to 3 duplicate ACKs, always set the window size down to 1. So you see the older version of TCP is very, very conservative as well. No matter what kind of loss it is, let's be very, very kind and gentle to the internet. Let's just slow down, okay, and restart. Okay. Note here, when we detect loss from a timeout, you see, starting from window size 1 and increasing exponentially until threshold. What is this? This is slow start. So a timeout loss is really, really bad. It's triggering the TCP to reset itself, essentially. Okay. So this is to illustrate the behavior of TCP Tahoe, the traditional version. Okay, you see here, window size at the beginning initialized to 1, and it will increment exponentially until hitting the threshold, and then linearly. Upon detecting a loss, drop down to 1, increase in a slow start fashion exponentially, and then linearly. Now, how would TCP Reno react? So what will be the line of the congestion window size for TCP Reno? What do you think? Reno, does it start from 1? Slow start, yes, right? So initialize to 1. Also increase exponentially after threshold linearly. Oh, there's a loss here. Oh, but wait a minute. Reno decides how to drop depending on what kind of loss it is. So what kind of loss is this? Any guess? Those who say 3 duplicate ACK loss, raise your hand. One hand? One hesitating hand. Those who say it's a timeout loss, raise your hand. Okay, very good. Many. Why? Why? It dropped to 1. But hey, this is Tahoe's behavior, you see? Tahoe actually did not differentiate what kind of loss it is and just dropped to 1. Think again. Are you all thinking that, oh, the window size dropped to 1, therefore it's timeout loss? No, but this is Tahoe. Tahoe always dropped to 1. Guys, look at the timeline. Yeah, Jingyuan is also saying timeout. Yeah, you're just like the rest of the class. Okay, look at this. So I'm so glad that I asked so I can clarify. Look at the timeline here. So 1, 2, 3, 4. Each is actually counting a round of RTT. So this is 1 RTT later from a first time point. So window size incremented by the previous window size, so exponential. Now, you see, between the large window size and the 1 window size, there's only 1 round. Do you think this is long enough to fire a timeout? What is timeout interval? Well, it should be at least larger than the round trip time, right? And adding 4 times of the deviation. So this is definitely too short for a timeout drop. This is a duplicate ACK drop. And therefore, if I'm Reno, I will be what? At this point, detecting a duplicate ACK loss, drop the window size down to half, which is right there. Because we were 12, right? So drop the window size down to 6 and continue to grow linearly. So TCP Reno goes like this, going exponential linear, drop to half, and then linear. If you see TCP Tahoe's window size changing more like this, okay, reaching 12, and then something like this. After a couple round trip time, at least definitely more than 1 round trip time, and then drop back down to 1, then this is more likely a timeout loss, okay? In that case, RENA will also drop down here. Oh, by the way, hey, good question there, Shiwei. How is SS thresh determined? Because you see also in this plot, hey, wait a minute. SS thresh was 8 and suddenly 6. SS thresh is not a fixed value. It's also changing over time. Okay. And the timing of it needing to be changed is this. Whenever there's a lost event, SSH is reduced to half of the window size prior to the drop. Okay. So if you think about it, whenever there's a loss event detected, SS thresh is set to half of the window size. And the window size is reduced to either 1 or half of the previous window size. SS thresh is always dropped to half of the window size. It's regardless of what kind of loss it is. Okay. What does that mean? That actually meant that the designer of TCP think half of the window size is the point where TCP sender should start to be a little bit conservative increasing the window size. Be careful increasing the window size. Okay, so SSH thresh is actually changed in the middle of a TCP connection, depending on whether there are losses. Now the initial value, okay, in a couple slides you will see the initial value. It was typically 64K, I think, 64K byte. Okay, so that is saying that when TCP is starting up, the designer thought it should be okay to allow the window to grow exponentially until 64 packets. But nowadays, I think that is a little bit too aggressive. All right, so let me confirm one thing. When should the exponential increase switch to linear? Very good, very good. When the window size reaches SS thresh. Afterwards, linear. So to sum up, the finite state machine of TCP now capturing the congestion controls behavior is going to look like this. We do have 2 states. Okay, congestion avoidance and slow start. So on the left here is the slow start state. There are 4 different transitions. This is receiving a new ACK. We increment the window size by 1 MSS by 1. Okay. And then send the packet out. Okay. Here we do sort of clear the duplicate ACK count. Okay. But it's rather minor. If we receive an ACK, but it's duplicate ACK, then we increment the counter. When the count reaches 3, then what do? Reduce the window size to half, set the threshold to half, and then reset the dupe ACK count. Okay. So in the pseudocode here, it's a little bit tricky. We know SS thresh needs to be set to half the window size. And then we reset the window size. Okay. Given that SS thresh is always half window size, so yeah, it's okay in this case. Set the window size to SS thresh. This is also declaring that, hey, afterwards, window size increase linearly. Last transition is the timeout. Oh, this is the bad case, right? So SS thresh always drop to half the window size, and window size this time, it's not set to SS thresh. It's set all the way down to 1. Okay, and clear duplicate. Of course, retransmit the segment that's missing. Hey, wait a minute. Then how do we transfer from the slow start state to the congestion avoidance state? We just checked this. Check whether the window size is less than the SS thresh or not. In case it's not, then let's move to the congestion avoidance state. You'll see that, hey, receiving duplicate ACK incrementing count and receiving duplicate ACKs, the actions are actually the same. So how we drop the window size, it's actually independent of which state it is. As long as there's a loss, if it's this kind, drop to 1. If this kind, drop to half. Okay. Now, how do we return from congestion avoidance to slow start? Yeah, if we have that bad loss, right, we drop all the way to 1. So the timeout event being triggered at the congestion avoidance state is going to take us back down to the slow start state. So once again, new X. What are the differences? Oh, you see, over at the slow start state, the congestion window size is incremented by 1 per ACK. But here, it's incremented by what? The number 1 over the number of ACKs, the reverse of this. Reverse of this. So we have MSS at the top and then cwnd at the bottom. Is that correct? Yeah, we got it right in the middle of the lecture. And then we do have these timeout events where we set the MSS, the window size all the way down to 1. And we do also have the duplicate ACK stuff. Okay, retransmit faster and drop the window size only to half. All right, so this is the basic mode of congestion control in TCP. There's just one trick people added later after TCP Reno. It's called fast recovery. And it works this way. It addresses this very special condition, the duplicate ACK condition. So regardless of whether we are in slow start or congestion avoidance state, if duplicate ACK equals 3 is triggered. Whoopsie. Okay, so thinking about the time. Okay, let's take things slowly. So why don't we do the quiz first, and then we go on to talk about the fast recovery. So, quiz. All right. So this is quiz 23. Oh. EIMD versus AIMD. So what I am showing there is the basic form of congestion controlling TCP. And then I do have a case here on the right, host A and host B. A sending data to B. So the window size at the beginning was, well, actually it's in the middle of a connection. The window size at the time was 4 packets. SS thresh is A. Now, given that the window size is 4 packets, we're sending 4 packets out to B. So sequence number is 1, 2, 3, 4 MSS correspondingly. And each packet is exactly MSS bytes. But the third one is lost. Therefore, the ACKs B is sending back is just for segment 1 MSS, and then segment 2 MSS. 3 is missing. Therefore, 4 MSS is actually triggering a duplicate ACK. Okay. So the question is, starting from Q1, if the SS thresh is A packets, what will be the window size B when the sender receives the acknowledgement for 1 MSS? And what will be the window size C there upon receiving the second ACK? And what will be the window size D there receiving the third ACK, but a duplicate ACK? I actually saw there's a team already, right, posting on Slack something. Was it easy? Let me see. Oh, team 12. A9, 1 respectively. Oh, you already answered for 2. Okay. Are you sure? No? Okay. Ah, good. So then it's good that I actually slow down, because then you will have trouble following fast recovery. Anyone wants to try? What is the value in B? What do you think? Eating. 5? Do you agree? Uh-huh. It is 5, right? Because what? The SS thresh is 8, so 4 is definitely below 8, so we're in the slow start state. When an egg is received, we increment the packet size by 1, or 1 MSS. So now it's 4 MSS, so incrementing it by 1 MSS, so 5 MSS. Sorry, MSS. So that was eating, I think. Oh, now, what about C? Anyone? 6? Very good. Xu Shu Wei. Too easy? What about D? 7? Xu Shu Wei just says, no, 6. You think 6? Okay, how many of you agree with Xu Shu Wei? Okay, only 2, sorry. Okay, so James also? 1? James says 1. Very interesting. Something is lost, yeah. But, very good point. Did host A detect the loss yet? We know something is lost, but we are human beings, right? We are like God. But TCP sender has not yet detected the loss.
So after the timeout, so he can detect the loss.
Yeah. Very good. I think you see here, giving the answer wrong is completely fine, because that's a way also you're exploring what is the right way of interpreting the finite state machines. Okay, are we good? Okay, we did not detect loss yet, unfortunately, right? Because we are seeing, 1 duplicate ACK, and that's it. The timeout interval is typically very long, so what I'm drawing on the right of the side, that is saying, timeout interval, really, really long. Okay, so there's no way host A detect timeout, detect the loss because of timeout. So James, very good try. And I think team 12 also tried, very good. So trying is like answering it already, because making a mistake actually adds to the memory. So, by the way, Xu Shu Wei answered twice. Okay, but that counts only 1 quiz, okay? Okay, are we good? Now let's try Q2. So we just answered for Q1. Q2. Q2 is what? The case of... no. We should not be doing exponential increase. We should be doing additive increase, right? The tricky case. Because SS thresh is 4. Window size is 4. According to the state machine, we move to the congestion avoidance state. Now, at time point, we receive ACK 1 MSS. What should be the window size? Reacting to the ACK. Eating? All right. Brave girl.
Wouldn't size be fraction? I was thinking about 4 1/4.
Very good point. Very good point. When the TCP sender is sending packets, can it be a fraction? Hey, we're counting bytes. Why not? Because MSS is actually a value. Yeah. So fraction definitely works. Okay. So you're thinking, oh, wait, 4 1/4 packet, what is that? Well, it's actually 4 1/4 of the maximum segment size, 1,000 bytes. Okay. So that will be 4,250 bytes window size. Good. So I'm saying it out loud, kind of. 4 1/4. Did you also get 4 1/4? Not quite? Or am I wrong? Okay, 4 MSS, what does that mean? That means there are going to be 4 eggs coming back, right? So for each egg, we increment only 1/4 of an MSS. Because then after 4 eggs, 1/4, 2/4, 3/4, 4/4, 1 MSS. What about C? C? Xu Shuwei? Busy calculating?
I guess
4.5? Let me see. Oh, you calculate to some very, okay. Is it something like 305 divided by 68? So say it again. 4.5? 4.5. Okay, 差不多. 差不多. Turned out that it's kind of close. Shall we do the calculation together? So what do we have now? 4 1/4, isn't it? 4 1/4. Now we receive an egg. Well, this is essentially 4, 17. Okay. And we need to add a quarter of this to this size. So that will be reverse, right? And then 1/4 of it. Is it 1? Right. So adding this to this. Is that right? I think so. Good. And let me just not do the arithmetics, okay? So confirm the window size. And the new window size is the window size plus, essentially. Okay? Yeah, so all of these is followed by MSS. I know. Okay, think about this. This is the number of eggs, and therefore, this is the proportion of the window size you add to the original window size. Oh, wait, so no, it should be 4, right? Okay, sorry. I am confused myself. Okay, so this is still correct. No, no longer dividing by 1/4. 1/4 happened already before, okay? Receiving the first egg. So this is the right value. Just reverse it. And D, D should be the same as C because of receiving a duplicate egg. So the duplicate egg action is simply, counting the dupe egg count, and that's it. Window size did not change. Yeah, reverse of it. Good. So guys online, hope that you guys copy this as well. And then we really need to move out of this this lecture room because Professor Wang Hui, they need as well. Okay, good. So think about it. Tuesday, I'm gonna go over the state machine again because I need to talk about fast recovery, which concerns the finite state machine. Okay. Do you mind that that after we move out? Yeah, that sounds like it's if it's a quick question, then I can answer. Otherwise, that's way. Okay, good. Thank you.